Euler's method. We use the Euler's method to find the numerical solution or the numerical approximation to the solutions of the first order initial value problem, dy over dt equals f of t y, where the initial values when t equals t naught, y equals y naught. Suppose we are interested in this solution curve, which we cannot find an explicit formulas, which is the solution to the differential equation. And we are given the initial point x0, y0, and the rate, which is the derivative in terms of x and y. So we start with the point x0, y0, and using the derivative, which is the slope, we draw the tangent line at this point. We then pick another x values, x1, and we use the equation of the tangent line to estimate y1. But this is an estimate. Remember, y1 should be on the solution curve, so there is an error there. Using this point x1, y1, along with the differential equation, which is the slope, we can obtain another line. We then use this line to estimate the solution when x is x2. And if we keep repeating this process, we end up with a collection of points. These collection of points form a curve that estimate the solution curve. Obviously, the more points we use, the better the estimate. And also, the smaller the delta x, the better the estimate. The smaller the delta x, the smaller the error. To summarize the process, we first start with the point x0, y0, along with the slope. We find the equation of the tangent line. Then we pick the second x value, which is now x1. x1 is x0 plus delta x. And we use this line to find y1. That is, we plug x1 into this line. But remember, x1 minus x0 is delta x. So now we end up another point x1, y1. And along with the differential equation, we find another equation. This time, the linear equation is y1 plus f of x1, y1, x minus x1, where f of x1, y1 is the slope at the point x1, y1. We then use another x value, x2, and plug this into the equation that we just found to approximate y2. And remember, x2 minus x1 is the delta x. And then we use the new point x2, y2, along with the differential equation to find another line to approximate the curve. Now, we see there is a pattern here. This process keeps repeating, so we end up with y sub n equals y sub n minus 1 plus f of x sub n minus 1, y sub n minus 1 times x sub n minus x sub n minus 1. At any point, we would need to know the previous point. Y sub n equals y sub n minus 1 plus x sub n minus x sub n minus 1 is delta x. F of x n minus 1, y sub n minus 1. This process to estimate y sub n is called the Euler's method.